This is the fourth video on my ESP-IDF series, and in this video I'll be talking about how you can use ADC or analog to digital converter of the ESP32 to read analog input from different sensors or modules. Analog to digital conversion, or ADC for short, is the ability to read a voltage level between 0 and a maximum value and convert that analog value into a digital representation. The ESP32 has its own ADC integrated on the chip. It has two ADC units and supports a total of 18 pins. You should check the pin map of your own ESP32 that you own to see which pin can be used for ADC. It should have the tag ADC on it. Unlike the legacy ADC driver, ESP-IDF from version 5 and beyond has two modes. One-shot mode, the ADC conversion only happens when you instruct it. If you want to get the output 5 times, you simply call it 5 times. Continuous mode, where ADC conversion is repeated automatically at a defined rate. You can still use the legacy API and run older code, but this video will focus on the newer version. I'll be only talking about one-shot mode in this video. When you are working with the ADC pins, they are mapped to different channels as shown here. The first ADC unit has 8 channels and the other has 10 channels. If you can't find which pin corresponds to which signal name, you can look it up in the detailed pin list that I put in the description. Now I will move to some concepts you should know when working with ADC. The resolution of the ADC provided by ESP32 is 12 bits, which means that the measured voltage level is between the value of 0 and 4095. However, you can change the resolution or bit width used in your application from 9 to 12 bits. The attenuation of ADC refers to the voltage scaling factor that can be used when measuring voltage levels beyond 0 to Vref. Vref is the reference voltage used internally by ESP32 ADC. It differs from chip to chip, but the median is 1.1 volt. Furthermore, we can also use a calibration driver to get more accurate results. As I've said before, different ESP32 chips may have different reference voltages, and thus setting up calibration can minimize the effect of this behavior. The next part of this video will be a brief walkthrough of the API. Note that we are using one-shot mode in this video. We first include the necessary header files, then we create a handle where we have to specify the ID, which is either ADC1 or ADC2, and whether we use ULP or ultra-low power coprocessor in our project. You can also adjust the clock source, but normally we just use the default one. Then we create a channel configuration with its bit width and attenuation value. We call ADC one-shot config channel to apply it on a specified channel. Note that you can apply the same config with the same handle to multiple pins or channels. Once done, we can get the raw reading of the ADC. The relation between the ADC raw result and the voltage level is presented in the formula. But again, we can perform further calibration to get a more accurate result. We create a calibration unit handle and then configure a fitting scheme. The curve fitting scheme is available for the ESP32C3 and subsequent products, and we would use a line fitting scheme in this example. The configuration must match what we've configured for the ADC channel. After this, you can convert the raw reading to a voltage level in millivolts. Let's apply this to measure ADC input from a potentiometer using ESP32. Wire the left pin to 3.3 volts, the middle one to pin IO26, and the right one to ground. We must first change our C makelist file to include ESP-ADC as one of the components that we're going to use. Then we include the necessary header file. In our ADC reading task, we first set up the ADC handle unit to use the second unit, as IO pin 26 can also be used as the 9th channel of ADC unit 2. We then configure the channel to have a bit width of 12 bits and an attenuation value of 12. The default bit width should also be 12 bits. Then we create a line-fitting calibration scheme with our configuration matching that of the previous ADC channel configuration. In our while true loop, we repeatedly measure the raw ADC reading and the voltage level after calibration, and then display them to the serial monitor. I'm going to put the delete functions to free the resource as a demonstration, although they are not going to be called here. Flashing the code to our ESP32, we can see that when we rotate the knob of the ESP32, the value displayed on the terminal also change. The value of the raw reading ranges from 0 to 4095, which is also when we can't no longer change the knob to either the right or left side. The maximum voltage level after calibration seems to be 3.1 volts, which makes sense considering that we give 3.3 as the source. And that's it for this video. Stay tuned for more upcoming videos and don't forget to like, leave a comment, and subscribe if you've learned something new from my video.